When we graph this function on our graphing tool, we'll get a graph that kind of looks like this. So we have this portion here, and based on this portion here, looks like we have all real numbers as our range, and then we also have this section here. So we can confirm from the graph that the range is all real numbers. Now make note that we will not be doing a lot of range analysis because it is a little bit harder than doing the domain analysis. So given the graphs of the function, we have f of x, which is a linear function in the numerator, and we have a g of x, which is a quadratic function in the denominator, and we want to determine the domain of the q of x. So here the domain of this is going to be all real numbers, and that's the numerator. Here the domain is all real numbers. However, it is in the denominator, so we have to be aware of where it crosses the x-axis, because this is when the denominator is going to be equal to 0. So if I put g of x equal to 0 in the denominator, I get restricted values. So then the domain of this quotient function then becomes, I'll write it like this, the domain is going to be x is all real numbers, except for x is not equal to, in this case, -2, +2. Okay, so this becomes a new domain of this reciprocal function, and it's based on the restrictions in the denominator. So when we are doing domain and range of when we're combining these functions, we have to kind of think of what are the non-permissible values. So what are going to be values of 0 in the denominator? Sometimes we're dealing with square roots, so what inside the square roots can't be negative. So we have to kind of think of the non-permissible values in the domain of the functions. And we want to see how the functions combine algebraically. Okay, so for example, if we have two linear functions that are multiplied, well, that just gives a quadratic function. It gives us a familiar function. So when we combine them algebraically, we want to see if it generates a familiar function. And lastly, we can also combine the y values numerically, and just to give us some coordinates to see if we can establish some sort of patterning. So looking at this next example here, we want to state the domain and range, and really just mainly we're going to focus on the domain of f of x and g of x. So the domain and range of f of x and g of x, so the domain here is going to be the restriction x can't be equal to 3, because we're going to divide by 0. And since it's a reciprocal function, we know that it doesn't cross the x-axis, and it has asymptotes along 0, so y is not equal to 0. For g, it has a domain restriction because we cannot square root negatives, so x must be equal to or greater than -2. And as a square root function going up to the right, the range is going to be y is greater than or equal to 0. Okay, because that's the starting point of that function. When we combine these, we end up with 1 over x minus 3 plus the square root of x plus 2. So this is a new function. And when we look at the domain of this new function, we can use the most restrictive parts of the combined function. So we can't let x equal to 3. And we know that x must be bigger than or equal to -2. So it's got to be on the right-hand side of -2, but we'll have a restriction at x equals 3. So x cannot equal to 3. If we were to predict what this graph looks like, well, we really don't know what this graph is going to be doing, but we should start analyzing this. So first thing is, we know that at -2, there's kind of a domain boundary there. We also have a vertical asymptote at 3. So we know that on this side, there's nothing going on. Okay, so -2. So that's going to be the starting point of our function. And so we can maybe start making a table of values here. At x equals -2, we're going to end up with 0, -1 over 5. So it's going to be some point right about there. Okay, so that's an endpoint. We know that it should follow the asymptote. Okay, so it's going to go down to the asymptote down here. This also should come up along the asymptote here. But what's going to be happening as x gets really big? Now, as x gets really big, so I'm going to write it this way. So the limit as x gets large of 1 over x minus 3 plus square root x plus 2, this term goes to 0. So as that term goes to 0, the graph starts to behave like the square root function. So at some point, although it's going down along the asymptote, it's got to have to turn around and start behaving like a square root function at some point. So this is what the graph is going to look like. Now this is something not familiar to us, so if you didn't recognize this, that's okay. But we want to start kind of thinking about what the graphs look like, and then we want to draw them. And it's important to actually draw the graphs to see what these graphs actually look like. So when we punch this into our graphing tool, we're going to end up with x minus 3 plus, and I'll type in square root x plus 2. Okay, and we end up with a function. Oh, we do have a 0 here, so when I look at this graph, it does go like this. It comes up and down, and it's kind of exaggerated, but it does go down, and then eventually it does go back up like that. Okay, so there is a bottom to this function, and it does go back up. Now I've kind of exaggerated this a little bit, but if you change the scale of your graph, you'll see these kind of features where it kind of goes down, and then it's going to start going back up as a square root function.